Before working with trigonometry in 3D, we have to define some things about angles in 3 dimensions. First, let us define what is meant by the angle between two planes. And so we have to find out how is this angle defined. Let us start by looking at the line of intersection of these two planes, and then let us draw a line in the first plane here that is perpendicular to the intersection line, and another line in the other plane that is also perpendicular to the intersection line, and that intersects with the other line L1. And now the angle between the two lines L1 and L2 is just the angle between the two planes. To understand why this is the case, let us turn the whole situation such that we look directly into the line of intersection L. This means that the line becomes just a point. Let me now write this down formally. Let L be the line of intersection of planes P1 and P2. Then the angle between the planes P1 and P2 is defined as the angle between the lines L1 and L2, where L1 lies in plane P1 and L1 is perpendicular to line L. Line L2 lies in plane P2 and is perpendicular to the line L, and L1 and L2 intersect. Now we want to look at the angle between the line L and the plane P.
Now we want to look at the angle between a line and a plane. So we have to find out what is meant by the angle between a line and a plane. Let us mark the point of intersection S between the line L and the plane. Then let us choose an arbitrary point A on the line A. And we want to find the projection of the point A on the plane. Projection means we take the line perpendicular to the plane passing through A, eine Senkrechte, ein Lot, from A to the plane, and where they intersect, there we have this projection point A dash. We connect then the point S and the point A dash, and we get the line L dash, and the angle between these two lines is exactly the angle between the line and the plane. Another way of finding this angle is to take the normal line to the plane, this means the line perpendicular to the plane, passing through the point S, and then have a look at the angle between this normal line here and the line L, and we see it's 90 degrees minus the angle that we're looking for. So if we find this angle, we can just take 90 degrees minus it, and we'll find alpha. Let us visualize this by turning the situation such that the plane becomes just a line.
Let us formalize this again. Let A be a point on L and S be the intersection point between L and the plane P. Let then A dash be a point in the plane P such that the line AA dash is perpendicular to the plane P. And then let L dash be the line connecting S and A dash, and let N be a line perpendicular to P and passing through S. Then the angle alpha between the line and the plane P is defined as the angle between the line and L star, or as 90 degrees minus the angle between the line L and the normal line N. Let us now look at an example. We're given a pyramid with apex S, and here we have the point B as a vertex, M is the center of the base face, and A is the midpoint of this side edge. We have to find the angle alpha between the base face and the lateral face, Grundfläche und Seitenfläche, which is this angle here. And the angle beta between the lateral edge, Seitenkante, and the base face, Grundfläche. To find the angle alpha, let us look at this blue triangle here. Let's copy it over here, and we see this side length, the adjacent to alpha is 3.5 and the opposite is 11, so we need the tangent. This side is 3.5 long since it's the half of the side edge, and we find out the tangent of alpha is 11 divided by 3.5, and applying the arctan we find alpha is 72.3% the degrees. To find the angle beta, let us look at this triangle here, drawn over here, and we see we're missing this side length here. This means between M and B, and this we can calculate using this small triangle here, shown here. It is a right triangle. Both cathetas here are 3.5 since they're half the length of the base edge, and using the Pythagoras we get in the end x is 3.5 times square root of 2, which is exactly this x here. Now we know the opposite of beta and the adjacent of it, so we can use again the tangent, which is 11 divided by 3.5 times square root of 2, and using the arctan we get approximately 65.8 degrees.